A coder I admire named Dora keeps using Compiler Explorer. She's much cooler than me, but I think I can be quite as cool if I just learn assembler. So, whose assembly knowledge is as bad as that limerick or worse? Okay, most of you, good. My assembly knowledge is about at that level, but that's fine. In order to use Compiler Explorer, you don't need to be an assembly expert. So my name is Schau Knatten, and welcome to Just Enough Assembly for Compiler Explorer. This is very much an absolute beginner's introduction to assembly and X86 64 and the calling convention. So if you know a bit of assembly from before, there's probably not much new, so there's still time to escape. Who has used Compiler Explorer before? Also known as Godbolt after its creator, Matt. Yeah, quite a few. Who has seen it used in conference talks or like on YouTube videos or stuff like that? Quite a few of you as well. So I saw on Twitter a few weeks ago that Jason Turner had a little Twitter poll saying, are you planning to use Compiler Explorer in your upcoming C++ related presentation? Or did you use it recently in a presentation? And the options were no, yes, not presenting, or just show results. And you can see of the people who are presenting, more than half say they're going to use Compiler Explorer. So this is not very unscientific, right? It's very prone to selection bias, is tagging Compiler Explorer there. But it shows that there's quite a lot of interest in Compiler Explorer these days. So what's good about Compiler Explorer? You can take your C, C++, or Rust, or some other languages as well, paste it on the website, and you can see the assembly output from the compiler. Now, why is that interesting? It's interesting because you write your C and C++ code, or other languages as well, for other humans to read, and then the compiler translates it to the CPU. And it turns out that the CPU instructions that the compiler will give the CPU, they correspond to assembly instructions. So if you can see assembly instructions, you know what the compiler did to your code, what is it going to feed the CPU. What's also nice is that you don't only see one compiler, you can have several compilers. So you can compare Clang to GCC to MSVC, and you can put in different options. So you can say, okay, what happens on 01, on 02, 03, etc. So it's really quite flexible. So let's just start with having a look here, and that's probably way too small. So yeah, here's just a bunch of assembly code and some C code, and I'm not going to read through it right now. What's interesting is here you can paste your code, and then you see the assembly output. And you can see that, okay, so here's a function called computer. Well, here is the assembly code from that function. And if I scroll down, I can see here's the assembly code for the caller function. So you kind of can, and you can see also if I hover, it will highlight the lines of code that the assembly came from, and the other way around. And it's color-coded it, and it's trying to be really helpful to allow you to correlate your code with the assembly output. There's a lot of stuff here on the right, but in 50 minutes, you're going to understand every line to the right here. And I'm actually not going to go fast either. So still going to go quite slowly, but still you'll be able to understand why it's doing all of these things. So let's not read through all of it, but let's look at, okay, there's some things that seem to be going on a lot. So these D word putters seem to be important. And you can see EDI and ESI is used here both in computer and down in caller. And it's pushing and popping RBP. Yeah, so lots of stuff going on, and let's learn what all of this is about. So for today's talk, it's mostly going to be stepping through assembly in a toy debugger, in like a toy slideware emulator. So yeah, before I start, if there are any questions, please ask the questions while the code is up here. So don't wait until the end. It's better to, because we're going to have a lot of code on the slides, so ask while the code is there. So in my little toy assembly x86 emulator, in the middle of the screen is the CPU. And the CPU has a bunch of registers. We have some special registers, some general purpose that we can use for whatever we want. And in order for the computer to do anything interesting with data, it needs to get the data into those registers. So that's going to be our main focus. And we're only, for each example, going to show the relevant registers. So if we have an example using only these RDI and RSI registers, we're only going to show those to not just bloat the slides. And we're going to initialize them to 0 for each example. That doesn't happen in reality. It just makes the examples easier to follow and show everything in hex. So let's get some assembly code up. So here's our first assembly program for today. It has 3 lines of code. And each line has an instruction to the left and 0 or more operands to the right. And I put a little indicator. So what's this doing now? Thank you. Okay, here we go. Put a little indicator so we can step debug through the code like this, right? Just like in a normal debugger. And yeah, so let's start with the first instruction. It's a move instruction. And just like in C++, move doesn't move. In assembly, it means copy. So it's going to copy one of these operands into the other one. And in this case, it's actually going to copy the second operand into the first. And that's because we're using Intel assembly syntax. There are other syntaxes for assembly. Intel maybe feels a bit backwards because it says move RDI2. That means move 2 into RDI. There are other syntaxes that are the other way around, but I think Intel is the most readable one in other respects. It's the default one on Compiler Explorer, and I think it's the one that people tend to prefer these days. So the first instruction is a move instruction. It asks us to move 2 into RDI. And when we execute that, we can see we got the value 2 into the register called RDI. Then we move 4 into RSI. And then there's the add instruction. I guess you can guess what the add instruction does. It adds its operands together. And we are used to, in our high-level languages, saying like result, or int result equal a plus b. In assembly, the result goes in the first operand. So it's more like RDI plus equals RSI. So if we execute that line, it will add together the 2 and the 4 and put 6, the result, in the first operand, RDI.
The name RDI, RSI, are they any meaningful?
I don't know about those names. Like many of the registers have some meaningful names.
So it's like normal R0, 1, 2, and 3 on the PT.
Yeah, they have some very common usages, these two. But I'm not sure actually about their names. Remember, I'm not very much better than the limerick, so no too tricky questions. Okay, so that was registers. We also need to use memory, right? We have 16 general purpose 64-bit registers. Not much you can do with that, so we need some memory as well. So I put some memory on the right-hand side here as well. So these are memory addresses. They're actually 64-bit long, but I don't want to bloat the slides, so let's just show the last 2 bytes. And here's the value at that address in memory. And today we're going to focus mainly on the stack, but everything about addressing memory on the stack that I show today is going to be exactly the same if you want to address some other memory. It's the same things, but we'll use the stack mostly today. So on this architecture, the stack grows downwards. So our stack is like coming from up here, and it's growing down here. And there's a new register, RSP. That's the stack pointer. So that has a very good name, I guess. So we have the RSP is the stack pointer. It happens to currently point to B0 in memory. So I put a little pointer here as well. RSP is pointing here. So this is the top of the stack. But as the stack is growing downwards, the top of the stack, when you push stuff on the stack, the top is going to go down like this. So it's a bit, might be a bit confusing. So yeah, let's first put a value in a register. So let's just put this literal value here, an immediate value, or yeah, put it into RDI. And I just picked this number because it's very easy to see the different bytes and see where they end up at the end. Now, then we're going to push. What are we going to push? We're going to push RDI on the stack. So when we push a register, we're going to copy the contents of the register onto the stack and then bump the stack pointer. So we're on X86 64, 64-bit registers. So how many bytes are we going to push on the stack and increment the stack pointer with? 8 bytes, 64 bits. And the second question is, so okay, where are we going to end up? RSP is up here, and we're going to subtract, actually, since it goes downwards, subtract 8, we get down to A8. And what's the value of that byte going to be? There's one correct answer, and there's one wrong but plausible answer, and the rest are just plain wrong. Yeah, so those are both. Yeah, so the 8086 has a little endian architecture. So that means when you design a CPU, you have to like decide on which bytes go where. So a little endian architecture means the least significant byte goes on the lowest memory address. So if we execute this line, you can see it bumped RSP down here and put the number in. On other architectures, the answer could be FE, because there's no reason why it has to be in a certain order in memory. But that's how our architecture is. Yeah, then we can pop. So I skipped ahead a little bit early. We can also pop. We pushed RDI, so now we have these bytes in here. And then we can pop them into another register. So now we have popped some stuff off the stack again. So if you want to implement a little stack machine or something, that's all well and good to push and pop values, but we have random access memory. We want to be able to randomly, or at least arbitrarily, access our memory. So let's see how you can address specific memory addresses as well. Let's just put some 64-bit values into RSI and RDI. And then we see the move instruction again. So move instructions can be used for both memory and for registers and stuff. If you see here, it has the second operand is RSI, so it's going to copy from RSI. And all of this is the first operand, so it's going to move into whatever that means. And what does it mean? It says Q-word putter. That means a quad word pointer. So a byte, 8 bits is a byte, 16 bits is a word, 32 bits is a double word, and 64 bits is a quad word. So Q-word putter means this is a pointer to a 64-bit something. And where is it pointing? It's pointing to RSP minus 8. So if you go over here, RSP, subtract 8, we get down here. So this is saying, this is the address of RSP minus 8, so A8. So we're going to move the contents of RSI onto that memory address. So it looks exactly like when we pushed the thing, but we now explicitly put it at exactly that address. So we could have put it at any address, really. The add instruction also supports having one of the operands be a memory address. So it's exactly the same expression as we saw here. A pointer to a 64-bit value at this location. Take that, add it to RDI. And as we saw before, add will just store it in the first operand. So RDI is 22222, 3333 from here. Add it together and put 55555555 in RDI. So if we were in C or C++, this is how a local variable on the stack looks like. So this is how it would look like exactly if we had a long L equals 33333 in C or C++ or whatever. Then this is how it would look like. So before we continue, I want to say a few things about register sizes. So when the original 8086 came out, that was a 16-bit architecture with AX, BX, CX, etc. registers. They also gave us the option to only address the lower half with A low and AH for the high part of AX. So if you put something into AL, that's actually the same as AX, it's just using the lower half. And AH is using the high half of it. So it's actually the same physical register in there, just different ways of addressing parts of it. Then the 386 came along with 32 bits, EAX. You can still use the smaller ones. And finally, AMD came along with the 64 one, a 64-bit one, and then we got RAX, etc. But you can still put things in the lower parts here. So those of you who know me know I like C++ quizzes. I have a site called cppquiz.org. So here's today's C++ quiz. How big is an int? That's the correct answer. Yes, it has a size. That's correct. One or more. So it turns out the only requirement in the standard of C and C++ is it has to be 16 bits or more. I used to think it had to be 7, but it turns out it has to be at least 16. Int has to be at least as big as char, and char has to be 16. Yeah? Oh, the short, I mean, yeah, short, sorry. Yeah. It has to be at least as big as short. And actually, I think actually int, yeah, short has to be 16, doesn't it? Yeah. Anyway, on my computer, what's int going to be on a normal X86 64 machine? How big is an int on my machine? Yeah, 32 bits. So when they went from 32 to 64 bits, they didn't want to change the size of int, so it's still 32 bits. So this 64-bit thing corresponds to a signed or unsigned long, and you can put a signed or unsigned int here, signed or unsigned short in here, and a signed or unsigned or just plain char in these ones. So let's do, if we skip back, this example we just did. Let's do exactly the same example, but with smaller register sizes. So let's use the 32-bit variants. So we're still displaying the full RSI and RDI, but let's use the 32-bit ones. So ESI and EDI. And those you see a lot because int is kind of our default go-to data type. So you see ESI and EDI a lot. So let's see what happens when you use those. Well, we move 333 into our ESI, which is the lower half of RSI. Put 222 into EDI, the lower half of RDI. And then we're going to put one of our registers into memory. And now we're using D-word putter, double word pointer, not a quad word pointer, because now it's only a 32-bit register. So this is a 32-bit register. So let's use a 32-bit address, RSP -4. So it goes in here. So we only needed 4 bytes for the int, so we saved half the memory. And then we can add it just like before. We can add whatever is on this address to EDI. So we end up with 55555. Yeah? Yes, they should. Yeah, thank you. So that's referring to these here. Should be 333 instead. So now we can read and write both longs and ints to memory. But that's not enough. We also want to have more data. We want arrays. And arrays are nice also because we get to see a bit more advanced memory addressing. It's a good motivating example for that. So let's just put some values in memory. So RSP -8 gets 1111, then RSP -2, 6, -4, -2. So now we have some bytes in memory. Assembly doesn't have any type. Yeah, I use the word here now. So just because I don't want the memory to grow too big, I'm using shorts. So word is 16 bits. So then we save some space on the slides and see some other register sizes. But assembly doesn't have types. These are just bytes in memory. So assembly doesn't remember that I put a 16-bit value there. It's just bytes in memory. They could be anything. So these could be 8 bytes. They could be probably what we want to use them for, 4 shorts. They could be 1 long. They could be some part of a string or a network packet or a class or a structure. Or they can be anything. But we're going to treat them as an array of 4 shorts. And arrays are like, they're almost pointers, right? So if you want to do something with an array, you want a pointer to the first element. So let's say it would be useful to put a pointer to the beginning of the array in a register. So let's say we want to put it in RDI. So how do we find that address? Well, we already saw the square bracket operation thing. We could do RSP minus 8. So RSP is here. There's a stack pointer. Here's our value, or our first value in the array. Then you can use the LEA instruction, which is the load effective address instruction. Very handy thing. It will compute the address just like we saw it was doing here. But instead of dereferencing the value, it will just give you the address and put that into RDI. So now we have a pointer to the beginning of the array, and we can start using it for something. So let's say we want to, OK. Yeah? I think you have to put the square brackets for the syntax to be correct. Yeah. Yeah, so say we want to get at the fourth element in the array. What you do, you have a pointer to the beginning. You have to skip past element 1, 2, and 3. They're both 2 bytes long. They're short, so we take 3 times 2 is 6. So we can get to RDI plus 6 and get the fourth element in the array. Then we can move it into, for instance, AX, just to show some different sizes again. AX is the lower 16 bits of RAX. But we don't want to hard code the array index in our assembly code. We want to be able to maybe change where we're pointing to. Maybe we want to be able to iterate through the array. So it would be really useful to have the array index in another register. So let's use RSI as the index register and say we want the first element of the array. So the first element is index 0. Let's put 0 into RSI. And now we can see a bit more advanced addressing here. So RDI is still the base pointer. Then you have the index and size of short, basically. So if you want to get at the RSIth element, you have to multiply it by 2, the size of short, to compute the address. So 0 times 2 is 0. So we're getting the element at index 0. We're getting 1, 1, 1, 1, 1. But now we have parameterized it. Right? This exact line can now take the index from a register. So let's increment our index. Our index was 0. We increment it with the increment instruction. Now it's 1. Then we can use exactly the same instruction to do base pointer plus index times size of the element. And then we can move that into AX. So now we get 2 instead. And now we have generalized the way to access memory by the base pointer and the index. And that's kind of begging for being used with like conditionals or loops or something like that. So let's look at conditionals. We want to write an if statement which takes 2 numbers, checks if the first one is greater. In that case, it stores true. If the first one is not greater, it stores false. Quite simple. But in assembly, we don't have if or switch or else or anything nice like that. We have comparisons and goto, basically. But gotos are considered great. So let's see what we can do with goto. Let's move some values into registers. RDI and RSI are now 3 and 2. Then we can compare them. And nothing happened when I executed the compare. It just compares. It doesn't return you anything. It just checks various properties of comparing these numbers and just stores it away in some flags, in a flags register. On the next line, I can do a conditional jump. So I can do jump if greater. JG is for jump if greater. So it will check those flags that were set on the previous line and see, well, was it greater? RDI was greater 3, greater than 2. So yes, I jump. Where do I jump? To a label. And this is how labels look. So I jump to the label. And we want to store true because the first number was greater. So let's move 1 for true into RAX. And now RAX contains true. If it was the other way around, if we had 2 in RDI and 3, my clicker stopped working. Yeah, there we go. 2 in RDI, 3 in RSI. Compare them, nothing happens. Jump if greater was RDI larger than 3. It was not. So we don't jump, we just fall through. We fall through into here. On the next line, we store false in RAX. But now we have to be careful so we don't fall through down here, right? The labels aren't protecting this in any way, so we have to do an unconditional jump to get out of the if to avoid the other condition. And you might notice here that like this was kind of our else block, the false thing, and this was our if block, the true thing. So often you'll see that the else block is above the if block. There's a bunch of comparison operators. Or there's one comparison operator, and there's a bunch of conditional jumps. So compare up 1, up 2 will compare these two. And then all of these will check the result. So if they were equal, you can jump equal, you can jump not equal, you can jump less, less equal, jump greater, and jump greater or equal. And I said assembly doesn't have types. So it doesn't care what the type of a byte is in memory or in a register or whatever. But comparisons are different. Like you have a bit pattern that can either be a positive number, or if it's a signed type, it can be a negative number. So you have to choose, do you want a signed or an unsigned comparison? So we have some unsigned comparison operators as well. And well, greater and less were taken, so let's use below and above instead. So here are the corresponding ones for unsigned. And the way the comparison works is it just subtracts the second operand from the first. That's basically all it does. If they were equal, the result is 0. It doesn't store the result anymore, but it stores the fact that it was 0. It sets the 0 flag. If this was greater than this, well, then it gets the subtraction results in a negative number, and then it sets the sign flag. So what these do are just checking the flags that the comparison left in the flags register. Okay, now we have variables, arrays, memory addressing, conditionals. We also want loops. And assembly doesn't have if and else and anything like that. Of course, it doesn't have while or for or do or anything like that either. We still have comparisons and our gotos though, so we can implement a for using that. So let's say we want to iterate over a value. We want to iterate from 1, so let's use RCX as our loop index. Set that to 1. And we want to accumulate a value in RAX. So let's initialize that to 0. Then there's a label, and then we compare RCX to 3. So this is our loop termination check. Is it 3? It's not 3. So jump equal will not jump. It was not equal, it doesn't jump. It just falls through, and it increments our result. Just to have something to do, let's just add the loop counter to RAX. Then we can increment the counter. So now that's 2. And we unconditionally jump to the beginning of the for loop. Are we 3 yet? No, we're not 3 yet, so we do not jump equal. Keep adding RCX to RAX. Increment RCX for the next round. Jump to the beginning. Are we 3 yet? Yes, we're 3, so we jump to the end of the for loop. So that's how we do a for loop. And can anyone translate this for loop into C? Yeah, let's see. So here's the C code. So we say int RAX equals 0, for RCX equals 1, RCX not equal to 3, and then we have the plus plus RCX. Then we can go RAX plus equals RCX. So that's how you can do a for loop. So let's look at a real example. Not this one, it's too large. Let's look at a smaller one. Simple sum function. Simplest function I could think of, really. Sum function takes 2 integers a and b, sums them together, and returns the result. Sum of a plus b, just return a plus b. Let's just bring all of that code on the right-hand side. It's a bit, it's not too long. Let's bring it into our little slideware emulator. So here's all of our assembly code that we got from, I happen to use GCC 9.1, but I can't imagine this would change very much with the other versions. So the first thing to think about with a function is how do you get the arguments into the function? That's the first thing you have to do. So it turns out there's a thing called a calling convention. I'm on a Mac. I wrote the presentation on my Linux computer. Both of those use the systemv AMD64 calling convention. The calling convention will specify, among other things, how do you get stuff in and out of functions. And Microsoft has their own calling convention. It's very similar to the systemv one. And it says the first couple of integers, you can just stick them in some registers that we agree on. So it says the two first integers should go in RDI and RSI. So whoever called the sum function would first put the arguments 2 and 3 that it wants to sum into those registers, then call us, because then we can just go and pick them up from there. Then we start our function. The first thing we do is to push a register onto the stack. We're pushing RBP. And the reason for that is, and then you can see, we push it here, and then we pop it at the end. And that's because it's our obligation by the calling convention to not destroy RBP. So whoever called us, we're probably using RBP for something. So let's make sure if we overwrite it, we have to restore it. And we are going to overwrite it on the next line. So let's push that first. Then we move RSP. Remember the stack pointer? We move RSP into RBP. The reason we do that, this you're going to see in all functions when you look at them. And Compiler Explorer, it always does this. It puts a copy of RSP into RBP. And that's because in many, many cases, we are going to start messing about with the stack pointer. We might be pushing and popping stuff. We might call other functions. We might need to change RSP. So it's very nice if we, in the beginning of the function, we just make a copy here. This is called the base pointer. Then we have a base pointer that points to the beginning of our part of the stack. This is our stack frame, our stuff. And then we can do all this relative addressing here, relative to RBP, instead of RSP in case that changes. In this function, we don't mess about with RSP. It doesn't change, but it seems that most compilers will always do this anyway. So what does GCC do? Okay, first a disclaimer, I didn't write this code. GCC wrote this code. So if you have any issues with it, take it up with GCC. What it's doing? Well, we got the two arguments here in RDI and RSI. It wants to move those into memory for some reason. So it moved them into RBP -4 and 8. So we got them copied in here and here. And this is actually good because these are our function arguments. There are L values. They now have an address. We can take their address. We can inspect them in a debugger. They are actual variables in memory rather than just being some values in registers. So if you're doing a debug build, then I guess this is fine. Then GCC wants to copy them back into registers. So it uses EDX and EAX to copy them back into. Then we add EDX to EAX. So 3 plus 2 equals 5. And then we have to pop RBP. Remember not to step on our caller's toes. So we pop that and we return. And return just sets the instruction pointer back to whoever called us. The missing piece of the puzzle is how do we get the return value out of our function and up to our caller? And again, this is the calling convention telling us that if you're returning a single int, I just put it in RAX, and then the caller will, after getting return back, can just look in RAX and expect you to have left the package in RAX. And then finally, we return. So if anyone thought that that was a quite cumbersome way to add two values, I think both me and GCC agree with you. So we can put in some compiler options. So let's try O2 Let's try 01. So even on 01, it decides to do this optimization. So it's now a one-liner. So we just do a one-liner and return. Remember LEA? Load effective address. So this is an instruction used for loading effective addresses. So we are not loading any addresses. Why are we using LEA? Well, it turns out that this is something you do a lot. So this is very, very fast to do arithmetic. You can do simple arithmetic in here. And again, assembly has no types. So if you just give it some values, we can just pretend one of them is an address. That doesn't matter, right? So we just kind of hijack LEA to do the addition. And the nice thing is, unlike the normal add instruction, which adds the result in one of the operands, we can choose where to get the result. So we can add RDI, RSI, the two registers that the calling convention gave us the values in, and put them directly into the register where we're supposed to put the result by the calling convention. So that's a nice little optimization that you will see a lot. So now we don't need to move anything into memory or back again. So optimizations are good. Then we've seen variables, memory, arrays, memory addressing, control flow, if and for, even started looking at functions. So then we can move on to the holy grail of programming paradigms, which is structured programming. Okay? Let's see what happens in a full function. So here we have our little sum function again. It's almost the same as before. Takes two integers a and b, sums them together, but multiplies them by 2 before returning. So our times 2 function just takes its argument, returns it multiplied by 2. So then we have our function a plus b, pass it through times 2, and then return. Yeah, I'll copy all of this assembly code. It's now starting to look a bit big, but most of it we've actually seen before, so it's not going to be so bad. We'll put all of that into our slideware emulator again, and we're going to need a bit more memory because we're going to call some functions and stuff. So I just added another column of memory. It's still just sequential memory, just going down here, A0, and then continuing again, 9F, oops, and continuing down here. So it's just to make it all fit on the slides. So first we push RBP. We've seen this before. Then we move RSP into RBP again to have like a stable base pointer to do our addressing relative to. This time we need it. This time we're going to change RSP. So we had to make this copy of RSP because we're going to mess about with it. And why are we going to change the top of the stack? Well, the sum times 2 function is going to call this other function. And when we call that function is going to start using the stack pointer and saying, OK, everything from the stack pointer on I can use. So we have to make sure we first bump that out of the way so that we have our own part of memory that we can write to and not get overwritten by whoever we call. So then we can see RSP got bumped all the way down here to this place. And now everything is exactly like it was in our first sum function. We got the 2 arguments by the calling convention in RDI and RSI. GCC wants to put them in memory, and then put them back again. And then it does the addition. EAX, EDX, and that in EAX, exactly like in our previous sum function. So EAX is 3, and we add EDX, so it's 5. Now it's our turn to call a function. So now it's our turn to think about the calling end of the calling convention. So we have to make sure the single integer argument that we're going to pass to the times 2 function has to be in EDI. So we have our result, a plus b, is in EAX. We need to get that into EDI before calling our function. And then we call. We just transfer control down here. And again, push RBP, move RBP, RSP. We've seen those now many times. We've also seen this. We take the EDI, the argument we got, put it into memory so we have a proper local variable, and put it back into our register. And even here on O0, GCC figured, let's not multiply by 2, let's just add it to itself instead, because that's faster. So we add EAX to EAX. So 5 plus 5 equals A. Then we pop RBP as we always do, and we return. So now we're about to leave the outer function. And we have to make sure the result is in EAX, because that's what the calling convention tells us to do. Well, it turns out we are just returning whatever we got from the times2 function. So here, we're just returning that, and that value happens to already be in EAX. So we don't have to do anything. We can just leave. And the leave instruction is a new one we haven't seen before. Like we're used to, if you're returning from a function so far, we've been used to popping RBP and returning. This time, however, we have messed about with the stack pointer. So the leave instruction will first restore the stack pointer. If I click on the right screen, it will restore the stack pointer by copying RBP back into it. And then it will do the pop RBP that we've seen all the times so far, and we return from the function. So again, that seemed like a lot of work. What happens if we add some optimization here? Turns out 01 is enough. It doesn't help to put on more. So let's first look at times2. It's supposed to multiply its arguments. So it did that very quickly by just doing add RDI, RDI, or EDI, EDI. It turns out that we can also use the load effective address here just to take this sum and stick it in the other register in one operation. So we don't have to first do the addition and move it into RAX or anything like that. So, sorry about that. What about the sum times 2 function? It gets its arguments in EDI and ESI. So let's add those together into EDI. So now A plus B is in EDI. And now it's actually inlined all of the times 2 function in here. So just basically copy-pasted the implementation of this one in here. So it does the times 2 thing directly here without having a function call. And then we return. So again, optimizations do help. So if we go back to our first example. Yeah, sure.
If you made the times 2 static, would it drop the whole implementation from the right side?
Probably, because then it wouldn't be visible outside the compilation unit. Oh, yeah, sure, thanks. Yeah, so the reason it keeps it is because if you compile this compilation unit and you link it to someone else, then even if you inlined the times 2, this signature still needs to be here in the object file so that you can link to it and call it from some other compilation unit. But if you make it static, it doesn't have external linkage. You can't link to it, so we can just remove it.
The reason the add is on the 32 bits and the LEA is on the 64 is because the LEA actually got addresses. It must use the full register.
Was that a question or a statement?
I'm asking if I'm
Okay.
understanding it correctly.
Yeah, so the comment is, like, why is it using RDI plus RDI and not EDI plus ESI? EDI plus ESI. And the hypothesis is that it might be because LEA needs a 64-bit address. That sounds plausible. I'm not sure. Does anyone know? Oh, it doesn't matter. Because if you write to ESI, it's going to zero out the upper part. So if it didn't zero out, it could be that there would be something else in the top. But well, we only store it in EAX anyway, so yeah, sounds like a plausible theory. Yeah, so Back to the original. I promised you that at the end of the talk, we were going to understand all of this assembly code. It's not the most advanced program I've seen, but it does have functions, for loops, assignments, returning stuff, calling other functions, if statements. It has like all the programming basics. And that's kind of the goal of this talk, is to cover the basics, to give you like a fundamental understanding that you can build on. So let's see. I'm not going to go through everything in detail, but if you look at this code after the talk, sit down, and you will recognize everything from what we've talked about. So let's look at the computer function. Push RBP, move RBP, RSP. We've seen that. That's the usual preamble. Don't destroy RBP. Take a backup of the stack pointer in the base pointer, so we can do addressing relative to that. D-word putter means this is a 32-bit thing we're addressing in memory. EDI and ESI, why those registers? Because those were the parameters. They go into those registers by the calling convention. And then we have a for loop. So in our for loop, we're just decrementing b until as long as it's larger than 0. So b has been moved from here into here, so we can compare that to 0. If it was equal, the for loop is done. So then we can jump down a bit. So this is our end for down here. If it wasn't equal, we'll do the body of the function. So we'll move a and b into these registers, add b to a, and move the result back into memory, and subtract 1 from b. So this is the minus minus b in the for loop. And then we jump to the beginning of the for loop again. So this is things we've already seen. And then it finally moves the result into EAX. Why does it move it into EAX? Because that's where the calling convention tells us the result should be. We pop RBP to restore it and return. Caller again, the preamble, not going to go through that. Setting aside some space on the stack, so whenever you see sub RSP something, it means let's reserve some space on the stack for ourselves. And again, we see ESI, EDI, so we have these literal values 1 and 3. So let's put those as the arguments. Let's call the function. When the function returns, the result will be in EAX. Let's put that into a local variable. So this will now be our I over here. Then we compare it to 9, because we're going to check if it's less than 10. So we decided to do that with a compare to 9 and jump greater. And then it will move the result in here. If it was less than 10, then we return I. And otherwise, we just go down to the end and return 10, as you see here. Then we do the leave. We need the leave now because we did mess about with the stack pointer. So leave will restore the stack pointer and pop RBP, and then return will return us back to our caller. So now we have everything we need to understand all of that code. So the goal here was to mainly, like, if you can have very simple code, you can actually understand the outputs. The other goal is to have a fundamental understanding of how these things work. So when you paste your code, you're going to have some instructions here that you don't understand. Good thing here to do then is just hover over it. And then you get a short description of what that instruction is doing. And you can go and search for it online and find more information. But hopefully after this talk, then you'll have at least some framework to help you understand those results. So some tips if you want to use Compiler Explorer for your own code is to actually show the slides. Hover the instruction to see a description, then Google it. And make a local standalone reproduction first. So if you have code which includes lots of other stuff and calls function, try to get everything into one CPP file that doesn't include any non-standard stuff. maybe you have some refactoring tools that can help you, or else copy-paste is good. Just try to mash everything into one CPP file and remove everything you don't need, and then paste it. Then it's easier to read. Sometimes you want to look at a specific feature of C++. It's often helpful to use int instead of complicated types. So in many cases, it's a lot easier to see if you just use an int instead of like some really complicated stuff, unless it has, of course, side effects that are important to you. And don't try it out on your full project, right? Don't inline your entire thing and paste it. It's mostly useful to look at very specific things that you wonder about. And yeah, I also wanted to ask if there are any other tips from the audience for using Compiler Explorer. Jason Turner might know something about this. Yeah, that's a good thing. Yeah, put it on Twitter or Stack Overflow or something. That's also possible. Yeah, you didn't have many questions during the talk, so there's some time left for questions. So, any other questions? Yeah, Björn?
You didn't show anything about the program counter and how it stores the return address.
Yes, that was, I was trying not to, to complicate stuff, but yeah. So Björn caught me cheating a bit, especially in this example. So when, just step back a few. Yeah, so when I call here, and then later I return down here. So how does it know where to return to? So what it does, it will actually push the instruction pointer onto the stack when it calls, and when you return, it will get that value back to know where it's going to. And in that way, you can call as many functions as you will until the stack is full. So yeah. Leave will do the pop RBP thing that we've been doing all the time, but in addition, it's gonna restore the stack pointer. Because we subtract 16 from the stack pointer here, and then we have to make sure we add 16 back before we go out. So the way it restores it is to take, well, we did take a backup of RSP into RBP here, right? So it's gonna copy RBP back into RSP, and then pop RBP. So if we go down, here, and yeah, so the first thing it does, copy RBP into RSP. So RSP is now back where it was, and then pop RBP. And yeah, there should have been an instruction pointer at least on the stack in between here, but then I would have to add yet another column of memory, and my slide would be even more unreadable. So I skipped that one. Any other questions?
Does the last example change if you optimize?
That's a good question. Let's optimize it. What do you want, O2? Yep, it does change quite a lot. So what does it do? It takes the first argument, so A, puts it right into the result thing, and then it tests if B is equal to itself. So this computes a bitwise logical AND. Yeah, so this is kind of like compare. I don't know what test does. Yeah, so test for 0. If it was 0, we jump to the end of the for loop, and then we can just return because we already had the result in here. EAX is whatever A was. If not, then we're going to keep adding ESI, which is B, keep adding it onto A, or onto the result, and do B minus minus. And yeah, here's another thing. I said that compare is basically a subtract, which doesn't store the result. So here's an actual subtract. And this is quite nice because then you don't have to first subtract and then do a comparison after. You can just jump if not equal. So subtract 1 from ESI. If it reached 0, it will set the 0 flag. So we can just test that down here instead of doing an extra compare. And caller, that's nice. Move EAX7, that's everything. So it will do some constant propagation and inlining and stuff, and just, return 7. And again, if we would make the computer function static, so we can't reach it from other compilation units, this entire thing gets pretty nice. So, yeah. Yeah, any other questions?
When would you recommend taking a look at examples in Compiler Explorer versus, for example, you have a bottleneck to just measure performance first and just think algorithmically and
Yeah, do the latter thing. Do measure. Because it's like this is what the compiler says to the CPU. Like, here CPU, do these things. And the CPU is going to say, yeah, sure. And then it's going to go do something completely different, right? It's going to reorder stuff, do branch prediction, and you get like cache things. So you can't really see, okay, are you trashing the cache or not? Like, all of those things are very important, and the algorithmic complexity. So I would at least not like use this as the truth for performance. But it can very often be useful to get some more knowledge about things. So I think Matt Godbolt, he said his motivation for creating Compiler Explorer when it was just a local command line tool he had was he wanted to check when they introduced range-based for loops. So are they going to be more expensive than just for I equals 0, etc. And then you could do both versions in here, and you can see the assembly is exactly the same. And then you can quickly check different compilers. And in that case, you can trust, well, okay, the range-based for loop is fine. He could use it in his high-frequency trading or whatever he was doing at the time. So for those things, it's nice. And for other things, it's just handy, or if you're curious. I did put out a tweet a month or two ago saying, what are some cool things you learned on Compiler Explorer? And I got no replies. And then Matt Godbolt retweeted it from the Compiler Explorer account, and then all of the yet more 0 replies came in. But hopefully you can actually use it for something useful. So I used it at work a little while ago. I was trying an approach where instead of using enums and switches, I wanted to use variants. So I would use a variant instead of an enum value. I would have several variants and see like how is that going to work? Is it going to be inlined as well as enums and switches? And it turned out that even with O2, it was doing function calls to std_visit. And I don't know how it's implemented or anything, but like, well, the enum and switch case was just like move some stuff in here and return. The other one was doing function calls and everything. And I thought, well, maybe that's not the best approach, even though I thought that was really clever. So yeah, you can do stuff like that.
If you want me to, I can add to the question that I found it useful to. Okay, I found it useful to test if something is worth going through with. For example, I have an ID that I think the compiler will be able to inline, and I can run it in do it in Compiler Explorer, test my ID, see that it's plausible. So I make the effort in the real program.
And then it's really nice if you see that, like you can open another tab. I have 1 minute left, so I'll do that. You can add, not here, we can go add new compiler. So here we can compare to GCC 9.2, or we can like see if we can find Clang. I think it's somewhere at the top. Let's see what Clang trunk does. And let's see, give it the same options. Yeah, so then you can compare. So like if Björn then sees that all the compilers he's interested in do the same thing, then that's a good sign. Jason?
I just want to comment on Bjorn saying it's plausible that it would be in line because he saw it on Compiler Explorer.
Yeah.
To be fair, and you already said this, measure.
Yeah.
Right? Because in the context of a large application, the inlining that you saw in Compiler Explorer may or may not happen.
Yeah, so it's a good way to test if it's plausible, as Björn says, and then you can measure. Okay, that's time's up, so thank you.